Okay, so when we developed our Bayesian methods for understanding how to demodulate BPSK symbols, actually we were still working only with this simplified model. And in fact, the essence of the demodulation problem is coming out very nicely in this simple model. If we add all of the complexities of the real practical system, then the essence of the detection problem somehow gets obscured. So that is, I would count that as a benefit of adopting this simple model of the BPSK or OOK demodulation. Now, one another benefit that we get from this simplified model is that we can actually uh, very nicely extend it to modulation schemes which are uh, more complex. And so towards that, okay, fine. Actually, before we get to that, let us do a quick review, a recap of the way in which we can evaluate the theoretical performance of a BPSK receiver or an OOK receiver in the presence of Gaussian noise channel using this simple model. And you may recall that the probability of bit error has a theoretical formulation which is given by the Q function, and the argument of the Q function is the ratio A divided by sigma n, where sigma n is the standard deviation of the noise, the square root of the variance. Uh, why this came about? Well, this was explained in an earlier lecture. If you look at slide 42 of this lecture number 3, you will see that there is a derivation of this particular formulation. But conceptually, what is going on is that we have our transmitted symbols S1 and S0, and remember the length of each of these symbols from the origin is this square root of this energy per symbol. And in this case, each symbol carries one bit. This symbol carries bit 1, this symbol carries bit 0. So each of the x's are getting mapped to one symbol. And so bit energy and symbol energies are the same. And therefore, the constellation S1 is located at positive square root of EB, energy per bit. And the constellation point for bit 0, S0, is located at negative square root of EB. And you will recall these conditional distributions that we were drawing here. The conditional distribution of R given a particular transmitted symbol is Gaussian shaped, and the probability of error is the area under this Gaussian PDF which is falling on the wrong side of the decision boundary. That is how actually, if you go to slide 42 of that lecture 3, that is how this Q function was derived. So essentially, if you evaluate the area of the conditional distribution of R given S1 which falls on the wrong side of the decision boundary, meaning that which falls on R less than 0, R which is negative valued, that area which is shown in this blue shaded region, that entire area is Q function of A divided by sigma n. Similarly, and so that blue area gives you the theoretical expression of the probability of error, because that area is essentially the probability that R is less than 0 when S1 is transmitted. And that probability is essentially the probability of making an error. And so similarly, the area in the green is the probability of making an error when bit 0 is transmitted. So with the probability which is equal to the green colored region's area, the receiver will make an error and say that bit 1 is transmitted where actually bit 0 was transmitted. The overall probability of error is the average of these two probabilities. But remember, these two probabilities are identical. You can see that by the symmetry of this diagram. Blue and the green have the same area. Uh, and so therefore, since the probability of error when bit 1 is transmitted is same as the probability of error when bit 0 is transmitted, the average probability of error is same as the individual probabilities of error, which is Q of A divided by sigma n. So again, a nice theoretical expression we can form for BPSK at least. I mean, this diagram is for BPSK. And actually we can develop a simulator that does what was shown on the very first slide over here. We can develop a simulator that does this, and then we can count errors, the number of times that the simulation shows x hat to be different from x that we have generated in the simulator. And we can evaluate the probability of error through simulation. We can experimentally evaluate the probability of error. And one of the very nice things, very pleasant, intellectually pleasing thing about this course is that something that you derive entirely analytically and something that you derive entirely experimentally by running Monte Carlo experiments, like what you did in lab 3. Both the answers come out to be the same. They are on top of each other. And so that shows us that, it shows us multiple different things. It shows that our simulator is correct. It is operating as expected. There are no bugs in your program. And second, it tells us that our theoretical understanding is also correct. Because the answer that we derived entirely by theoretical means, theoretical method, is turning out to be same as the answer that we derived by pushing theory aside and just developing a program which doesn't do any of this Q function or anything. But still both the answers are turning out to be the same. And so that is a pretty cool experience to have. The other benefit of this theoretical analysis is that it gives us certain insights about the operation of the modem. And specifically, it tells us that the performance of the modem, which is measured in terms of the probability of bit error, is dependent only on the ratio A divided by sigma n. Specifically, the absolute values of A and sigma n don't matter. Only thing that matters is the ratio. So for example, if you had certain value of A and if you scale it up by a factor of 5, so now it becomes 5 times A, the performance will improve provided the noise power doesn't change. But if the noise power also changes so that sigma n also becomes 5 times as much, then you are back to square one. You won't get any performance benefit even though you are transmitting 5 times higher voltage. So that is an insight that we can get by this theoretical expression. One technical note is that this ratio A divided by sigma n is sometimes expressed as square root of 2 times energy per bit divided by n naught. Where energy per bit we have already defined earlier, which is just the square of the length of the vector of a particular constellation point. So EB is something that we know. N naught is a new terminology. I think we have made use of it in the project, but we haven't really fully defined it earlier. So let us state it as that N naught is the power spectral density of the white Gaussian noise. Uh, and in this case, it is equal to 2 times sigma n squared. So that is our definition of N naught. Now, let us spend little more thought on this, uh, and then derive even more, a little slightly more deeper insights into the demodulation uh, strategy, or the theoretical implications of the demodulation strategy that we have, the minimum distance demodulator. So one insight is that the decision boundary between two constellation points is halfway between them. Again, here the assumption is that the transmitted symbols are equiprobable, and that most often is the case. So whenever the transmitted symbols are equiprobable, the decision boundary is halfway between the constellation points. We have seen this in the two examples. For BPSK, the 2 points are at minus a and a. Halfway between them is r equal to 0, which is where decision boundary is. Whereas for OOK, the 2 points are 0 and plus a. So the halfway is a divided by 2. And so the decision boundary is halfway in that case also. We are generalizing this and stating that that is the case no matter what. And we can prove this mathematically, either by using the maximum likelihood Bayesian approach or by using the minimum distance approach. So I will leave that detailed reasoning on and proof of this statement. I will leave it to you to prove it. The second point that we can make is that other than sigma n, suppose if sigma n, the standard deviation of the noise, is held constant, then the theoretical probability of the error depends not on the absolute place at which the constellation points are, but instead it depends only on the distance between the constellation points. And specifically, the probability of bit error can also be written as Q function of the distance between the constellation points divided by 2 sigma n. Or alternatively, because sigma n we have seen earlier is equal to square root of n naught divided by 2, it can be also written as Q function of d divided by square root of 2 n naught. Now d for the BPSK, the distance between two constellation points for BPSK was 2 times a. For OOK, d is equal to a. And so, although on the previous slide the theoretical expression was for BPSK, now we can very quickly write a similar expression for OOK. The only thing we will have to do is substitute d equal to a in this equation. But this statement is, we are saying it applies generally. It doesn't have to be BPSK, it doesn't have to be OOK, it can be any different way in which the transmitter can opt to place the constellation points. So here in this diagram I am showing 3 different schemes. Scheme 3 is the BPSK scheme with a equal to 1. And so the two constellation points are at 1 and minus 1. Scheme 1 and scheme 2 are not BPSK, they are not OOK, they are some other schemes. We are not even giving it any proper name. We are just calling them scheme 1 and scheme 2. The first claim is that the decision boundary, which is in the red, is between, halfway in between these 2 points. Blue corresponds to x equal to 1, yellow corresponds to x equal to 0, the red is the decision boundary. So no matter which scheme we pick, the decision boundary we will always draw halfway between blue and yellow. Again, that can be shown mathematically, which I leave it up to you. And the second conceptual insight that we are uh, formulating here is that the performance of these schemes don't matter on the exact location of the yellow and the blue dot. Instead, it depends only on the separation between the blue and the yellow. So the separation is 5 volt for scheme 1, it is 1 for scheme 2, and it is 2 for scheme 2, and it is 2 for scheme 3. Those are the values of D. And therefore, the probability of error expression for scheme 1 is 2.5 divided by sigma n, because D is 5. Probability of error expression for scheme 2 and scheme 3 is Q function of 1 over sigma n, because D is 2. So you will see that we are saying that the performance of scheme 2 and scheme 3 are identical. Although scheme 2 is having the constellation points which are different from the constellation points for scheme 3. The performance is identical. The question is, which of the two schemes you would prefer? Which is more efficient? Which uses less energy per bit on average and still gives you the same performance? Well, the answer is that obviously scheme 3 is preferred compared to scheme 2. Why? Because the average energy per bit for scheme 2 is going to be larger compared to the energy for scheme 3. The energy for bit 0 for scheme 2 is going to be 16. Energy for bit 1 for scheme 2 is going to be 36. So the average will be 16 plus 36 divided by 2, which is 26. So scheme 2 has an average energy per bit of 26 units, whereas scheme 3 has an average energy per bit of just 1 unit. So scheme 3 spends only 1 unit of energy for transmitting a bit on average, but still it achieves the same performance as scheme 2, which spends 26 times as much energy per bit. So scheme 2 is not energy efficient at all compared to scheme 3, and so that's why scheme 3 is preferred. Okay, now so these are the two main takeaways that again we are getting just by using this simple model. We haven't brought in the additional complexity as yet at all. Okay, now let us spend a little bit time in defining this power spectral density of white Gaussian noise. We won't spend a lot of time on this, but I think it's better to define it properly. And so what we will say is that the noise that affects the communication link is a lot of the times not only that it has Gaussian distribution, but also that it is spectrally white. So it is called white noise, white Gaussian noise. Whiteness and Gaussianness, these are two different things. Gaussianness refers to the probability density function of the random variable, whereas white aspect of the noise is in the spectral domain, it is in the frequency domain. The reason the light that we see is white is because it has all of the colors, meaning different frequencies representing different colors, they all are equally present. And similarly, this noise that we often encounter in the communication system also has power, equally strong power at all of the different frequencies. how much power there is at a particular frequency is what this power spectral density tells you. And so white noise, unlike many other types of noise and definitely different types of signals, has the same power no matter what frequency you pick. And that power is this N naught. The power spectral density is essentially the power that is contained at a particular frequency in a given signal. And that power at that frequency, you can kind of evaluate that power by squaring the Fourier transform of the signal or the noise at that frequency. So that is the general concept of PSD. Its detailed mathematical definition we won't be covering in this class, but we will say that for the white noise, the power spectral density is a constant number, n naught. The height of the power spectral density is n naught, and that holds irrespective of the frequency. No matter which frequency you pick, the power spectral density has that constant height. Okay, so let us stop here for this video, and then we'll come back and continue this topic forward in the next video.